ঠিক আছে Oh, you can talk normally. You don't have to whisper, like, you know. Huh?
You can hear from the other side of the room.
Acha, so transformers, right? So transformers, we've done up to electromagnetism in Rag porjonto. So er moddhe we've done stuff like Faraday's law, right? Lenz's law, and we've done those, and those are important for understanding concepts in used in transformers. Also, another thing that you'll have to remember is the concept of the presence of a soft iron core. Soft iron core thakle ki hoy? It concentrates flux lines, right? It pulls it through the soft iron, and transformers also need soft iron. Again, you can't use hard iron; that won't work. All right, so transformers. Describe the construction of a basic transformer with a soft iron core as used for voltage transformations. So it's called a transformer, Keno, because it causes changes or transformations in voltage. So that's why it's called a transformer. Transformer is obviously dui rokomer. Kiki? Yeah, step up transformers and step down transformers. So step up transformers basically increases the voltage, and step down transformers decrease the voltage. We'll talk about that in a bit more detail. Ekhane koyekta jinish I want you to notice at the very beginning. They use this formula: IP VP is equal to ISVS. Eta kotheke ashe? VI is what? Power. So basically what they're talking about here is the power transformation, or basically the power in a transformer and the power out. So what they assume here is that the transformer is 100% efficient. They do not use Ohm's law anywhere. So we're not going to use Ohm's law because in transformers we actually have two separate circuits. One for the primary coil, another one for the secondary coil. And when you mix these two up, that's when you have problems. That's right, yeah, right. Jeffrey. Anyway, so we're going to talk about this part first, and then we're going to talk about the other bits and pieces of transformers. So, first of all, if, okay, I'll try drawing a transformer. So if you take a transformer, it's basically what? It's a soft iron core, and you're going to have turns of copper wire on it. The wire is insulated, kintu. It doesn't touch the soft iron. It doesn't even touch itself, right? So basically ki hoy? Insulated wires are wrapped around the soft iron. So basically eta kotheke ashtese? It's coming from the concept of a solenoid. Solenoid to tomader mone ache, right? You guys remember this stuff. So what happens in a solenoid is, remember Lenz's law? Lenz's law te ki hoychilo? If you take a magnet, jeta north pole ache, if it approaches this soft iron core which is wrapped around with the metal wire, copper wire, as long as the magnet is moving, you get a change in flux, right? Which leads to an induced EMF. Induced EMF may lead to an induced current, right? So we start off with EMF and then current. Acha, so a couple of quick questions. What's going to happen if I move this faster? The change in flux will be more, right? And what's going to happen if I increase the number of turns here? Same, right? It's going to increase the EMF. So ekhane je jinishta tomader bojha dorkar is basically here we're using a concept which is Faraday's law. Faraday's law ki bole? That the induced EMF is equal to or even proportional to the rate of change of flux linkage. ঠিক আছে? So when you have the rate of change of flux linkage, when you have the rate of change of flux linkage, what do we say? It is proportional to the induced EMF. Right. So the induced EMF is proportional to the rate of change of flux linkage. So that's Faraday's law. So ekhane in transformers we use this same exact concept. If we were to draw it like, you know, in its separate segments, what the primary coil does is it creates a magnet along this end. North hole eta south hole. And the secondary coil is like another piece of soft iron, and it induces a magnetic field through this. Now, according to Faraday's law, you'll only get an induced EMF as long as there's a change in flux linkage. It's very, very important that you remember that this is all based on change in flux linkage. Keno? A magnet, coming back to this, a magnet, jotokhon tumi move korcho, totokhon porjonto you got induced EMF. Keno? Because that led to a change in flux linkage. Now the important bit is যে what's going to happen if you stop moving it? বলো? আচ্ছা, as long as you're moving it, you get an induced EMF because there's a change in flux linkage. Do you get that? But if you stop moving it, তখন গিয়ে কি হবে? There won't be any change in flux linkage. So if there's no change in flux linkage, you don't get an induced EMF, right? So one of the concepts that আমি বারবার বলতে থাকি is it's because of the motion of the magnet that you get electrical energy in the wires. So magnetic key energy is being taken from the wire, from the magnet. It's kinetic energy. Basically, it's motion, right? So it's not any sort of special energy, the magnetic energy or anything like that. Again, what you have is it's kinetic energy. So as long as it's moving, it has kinetic energy which can be extracted and be converted into electrical energy. So এখানে আরেকটা important জিনিস, if you notice it দেখবা যে তোমার এই ম্যাগনেটটা its motion will be opposed, right? So or motion যখন oppose হয়, so how do you oppose this? এটা অবশ্যই we won't go into too much detail. এটা নর্থ পোল যদি অ্যাপ্রোচ করে তাহলে এখানে নর্থ পোল হয়ে যাবে, right? এটা যদি নর্থ পোল সরে যায় তাহলে এখানে কি হবে? সাউথ পোল হয়ে যাবে. Basically it will oppose whatever motion it's trying to do. কেন? Because you're taking its energy and you're turning it into electrical energy. So basically it has to lose its kinetic energy. And how do you make it lose kinetic energy? By opposing its motion. This is basically the concept of Lenz's law, right? Lenz's law ki chilo. The induced EMF will be such that it will oppose the action which creates it, right? And this is true in all cases. It's always going to be like that. So, jai hok, coming back to this. So as long as you have a change in the magnetic flux, ততক্ষণ পর্যন্ত you'll have an induced EMF. So say the primary coil is wrapped around this. So তখন কি তোমার primary coil এর মধ্যে if you have DC, তাহলে কিন্তু এই চেঞ্জটা it will only cause a temporary transient change in the magnets, right? কেমনে? এটা before you switch it on, say you have a DC supply and everything. So এখানে before you switch it on, there was no magnetic field. When you switch it on, there's a change in magnetic flux in this part, creating say this magnet like this, and this induces an EMF in this, right? So if you were to have a primary coil which is connected to a DC supply and there's a switch, switchটা close করলে কি হবে? What would you observe? Come on, speak up. তো বলতে পারবা না? This is easy stuff. কি বাবা? Jeffrey বলো? Louder. বলে ফেলো। হাই নাই হয়ে গেছে। বলো জেফরি বলো। কোয়েশ্চেন কি ছিল? Oh my god. যাই হোক। So basically what you're going to see is if this is a DC supply, say এখানে like a second. So say this is a DC supply and you connect it to a battery, ঠিক আছে? And this is connected to a switch. এরকম একটা switch আছে. When you close the switch, you create a magnetic field. This will cause a temporary deflection. That's what I'm asking, right? So it's going to cause a temporary deflection in the galvanometer. Galvanometer deflection মানে কি? এর মানে হইতেছে এখানে একটা induced EMF হচ্ছে, right? But it's temporary, কেন? Because the moment the field is created, তখন আর deflectionটা দরকার নাই, because you only get an induced EMF when there's a change in the flux linkage, right? এটা বারবার বলতেছি because you understand. Induced current, if it depends. If this is a complete circuit, ঠিক আছে? তাহলে an induced EMF will lead to an induced current.
So you close the switch and open the switch.
If you close it once, you just get one deflection. এখানে
open it multiple times.
To get multiple deflections. So এখানে তুমি যদি একটা বাল্ব থাকতো, instead of this if you had a lamp here, কি দেখতা? ল্যাম্পটা জ্বলতো আবার বন্ধ হয়ে যেত। আবার when you open the switch, তখন কি হবে? If it's a galvanometer, it would deflect again, but first time যদি এদিকে হয়, second time it will deflect in the opposite direction. ঠিক আছে? Reason হচ্ছে because again when you're opening the circuit, you're causing a change in flux linkage in the secondary coil, right? মানে আগে ছিল কি? When you closed it, it changed from no magnetic field to some magnetic field. So this change induced an EMF. পরেরটায় what's happening is it's moving from some magnetic field to no magnetic field. যখন এই চেঞ্জটা হচ্ছে তখন what does it do? it induces another EMF, but it's going to be in the opposite direction because of Lenz's law. Yes, Jeffrey. Well, basically, আমরা চাইলে we could make a transformer like this. যে দুইটা তুমি bar magnet পাশাপাশি রেখে, bar magnet তো না, soft iron piece রেখে তুমি এরকম কাজ করলা. But the problem is the flux lines, all of the flux lines being emitted from this one might not necessarily pass through the secondary coil, মানে this one. সব যাবে না, তাই না? So to ensure that all of this passes through, one of the things we could do is we could take one rod, আর ওই একটা রডের মধ্যে we could wrap both of them. বুঝছো, primary coil and secondary coil. এরকম কিন্তু question আসে, ঠিক আছে? They sometimes draw transformers like this, ঠিক আছে? The first transformers ever to be designed were actually rings, ঠিক আছে? Rings wrap up করে তারপর এটার primary coil এইদিকে ছিল and ওইদিকে secondary coil ছিল. Do you get it? So আস্তে আস্তে this transformed into this, ঠিক আছে? It evolved and we eventually got this. Does this make sense to everyone?
So why we stop using the ring?
It's better to use, it's actually easier to use this. Easier to construct, more efficient, blah 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 blah. ঠিক আছে? হ্যাঁ। My God. Hey, you have to personal clear? Alright, fine. So now let's move on to how does it exactly work?
Sure.
Yes.
Then when we're asked to describe how the transformer works for the section between the primary coil and secondary coil, we just need to write the flux lines.
It's designed so that the flux lines pass through from the primary, and all of the flux lines pass
Just
from the
pass
primary,
from primary to
yeah, to the secondary. Take a sip. Yes, Jeffrey? Is it hold this up?
Okay, I tell you both spot.
No. Alright, তারপরে moving forward. So now going back to a transformer, what it basically is doing is you have an alternating current in the primary coil. So alternating current কেন সবাই তো বুঝছো, right? If you have DC, it's just going to work when you switch it on. And তখনই গিয়ে you'll have a momentary induced EMF in the secondary coil. However, it's going to go away the moment you, like a moment after you switch it on. So if it was a DC supply, you would have to switch it on and off, on and off, on and off. Then you'd get a blinking light here. So instead of that, what you could do is you could give a supply which is actually alternating to the primary coil. ঠিক আছে? So primary coil alternating supply দিলে কি হবে? This is our primary coil. So, huh? What? Anyway, so induced EMF so you have an alternating current in the primary coil which generates an alternating or constantly changing magnetic flux or magnetic field in the iron core. So when this field passes through the secondary coil, that's when we have a rate of change of flux. Do you get it? So this is the secondary coil. তখন কি আমরা কি পাবো? We'd get a lamp, say for example, which would be blinking on and off, right? Blink হবে. It's actually blinking. All the supplies connected to AC are actually blinking, but they're blinking at 50 times a second. 50 hertz. ঠিক আছে? ঠিক আছে, or 100 times a second. So যেটার কারণে the human eye can't detect any change. ওই যে sometimes করে না with your cell phone তুমি slow mo record করো, slow mo মধ্যে দেখছো হঠাৎ হঠাৎ এরকম blink করতে থাকে, brightness বাড়ে কমে. Why does that happen? Because the light source is actually increasing and decreasing. Alright? Does that make sense to everyone? Alright. Now the thing is that how do we make these transformers either step up or step down? ঠিক আছে, how do we do this? We change the number of coils. ওই যে আমরা যে জিনিসটা ইয়েতে দেখছিলাম এইখানে, according to Faraday's law, if you increase the number of turns here, তাহলে কি হবে? It would increase the induced EMF. So similarly here, what happens is if you increase the number of turns in the secondary coil, it's going to increase the induced EMF. So say the primary coil in this case has 100 turns, and the secondary coil has say 200 turns. So তাহলে গিয়ে কি হবে? The induced EMF will obviously double. So we can make a very simple formula from here. Ki hobe? Number of turns in the primary divided by number of turns in the secondary is equal to the voltage in the primary by the voltage in the secondary. Does this make sense? So if the primary coil had a voltage of say 12 volts alternating, the output will become 24 volts, right? Simple ratios. Does this make sense? Now, এটুক দেখে মনে হয় কি it's breaking one of the laws of conservation, right? Which one? Law of conservation of energy. How is it breaking it here? How is it breaking it here, bolo? It seems like the voltage is doubling, right? But আমরা কি জানি power has to be conserved, right? You can't create power out of anywhere. So what we can say, power in the primary must always be equal to the power in the secondary. And আমরা জানি কি P is equal to IV. So if that's the case, তাহলে কি হয়? I in the primary V in the primary must be equal to I in the secondary V in the secondary. So from this you can end up making another part of this equation. Jeta ki hoy, if you cross multiply this, is going to be current in the secondary divided by current in the primary. Is this clear to everyone? তাহলে এখানে যদি if the current was say 4 amperes, এখানে current তাহলে কত হবে? Is going to be 2 amperes. So it conserves the amount of energy in it. Does this make sense? Alright, at 2% clear? Okay. So this is basically how you make transformers work. So if you go back to the syllabus and see the points here, Kiki ase, describe the construction of a basic transformer with a soft iron core and use as voltage transformations. So voltage transformations are basically to make if you increase the number of turns, you're going to increase the voltage in the secondary coil. Be very careful. সবসময় ডায়াগ্রামের মধ্যে ওই ডান সাইডে যে secondary coil হবে এরকম কিন্তু কোনো কথা নাই. Sometimes you're going to draw the primary coil and you're going to automatically assume that this is the secondary, but sometimes the secondary coil can be on the left side. How do we know which one is the primary coil? It's the one which has the supply connected to it. Take it? And the secondary coil is the one which is connected to across the output. Alright, that's point number 1. তারপরে কি? Describe the principle of operation of a transformer. এটা তো বললাম. ঠিক আছে? So we'll talk about that again একটু পরে. Recall and use the equation VP by VS equal to NP by NS. এটা তো বুঝলা. Recall the equation via IP VP is equal to IS VS for 100% efficiency. Understand the term step up and step down. Describe the use of transformers in high voltage transmission and give advantages of this and why power losses in cables are lower when the voltage is high. Alright, so we just have a little bit left. Alright, so first of all, so how do we write an answer of how do transformers work? Key point like that. AC supply to the primary coil, right? তারপরে কি হয়? What does this lead to? It induces alternating magnetic field to pass generated by the coil to pass through the iron core, right? তারপরে কি? This alternating magnetic field passes through the secondary coil. তারপরে কি হয়? তারপরে this causes a change in flux of the secondary coil. Do you get it? Change in magnetic flux. Oh, shut up. Change in magnetic flux in the secondary coil. Do you get it? And this results in, this is the important part, induced alternating EMF. You must mention induced, you must mention alternating. Iron core. So induced alternating EMF. Does this make sense to everyone? So this then leads to an induced alternating current in the secondary coil.
There is only an induced current which is the circuit is complete.
You need a complete circuit. You just get an EMF. If it's an incomplete circuit, you just get an induced alternating EMF. And if you connect it to a circuit, this will lead to a current. Alright? Is everyone clear on this? Yellow. So, these are the points of the answers that you have to write. Tarpor asho. Next thing. Power transmission using transformers. Take a sip. So, power transmission ki hoy bolo? What do we have? We start off say with a power plant. Take a sec, guys. So power plant so basically what we do is so power plant generates you're using steam or whatever, generates power from the transformer, and say the output is 240 volts and say 10 amperes. Now one way of transmitting this is by using high voltage cables. এখানে যে বিশাল বিশাল টাওয়ার গুলো দেখো না, ওই যে ঢাকা শহর থেকে বাইরে হইলে দেখো না, you have all of those years and everything. So power plants are usually what? It's like really far away from the city. So at least a few hundred kilometers easily. So যেটা করা হয়, these cables have to transfer this electrical energy. If the current is high, even if the wire is like really thick and like really fat and everything, therefore the wire is going to have quite some resistance, right? So why does it have resistance? Because of its length. Resistance আমাদের মনে আছে equation কি ছিল? Resistance is equal to rho L by A. So A is really really long. It's in a couple of 100 kilometers easily. So তাহলে কি হয়? This would cause a huge amount of this energy to be lost. কারণ আমরা জানি power যেটা loss হয়, ঠিক আছে, if we want to calculate it, we could say P is equal to I square R, right? So, or you can also say V square by R, where V is the voltage from this end to this end. It's not going to be 240. It's going to be the difference of the voltage from two ends of the transformer, two ends of the cable. So if we take power is equal to I square R, তাহলে খেয়াল করো, we can work with this easily. So P is equal to I square R. এখানে কি হইতেছে? Basically 240 volts দিয়ে তোমার 10 amperes, it causes a huge amount of energy loss just by warming the wires. So one way of decreasing the power loss is by decreasing the current. So how do you decrease the current? Easy. What sort of transformer do you put here? Step up. Right? Always power plant এর কাছে যে ট্রান্সফরমারটা থাকে, these are always step up transformers, and these step it up by like a huge amount, so like a factor of say 1000. Usually it's easily above a million. So even if we increase it by a factor of 1000, you get 240,000 volts, and the current drops by a factor of 1000, so it becomes what, 0.01. I know. So step up transformer, so the ratio of the turns is 1000, so the voltage increases by a factor of 1000 and the current decreases by a factor of 1000. You get it? So that's basically 240 into 1000 and 10 amperes divided by 1000, so that the power output remains the same. Does this make sense?
This makes sense.
Stop doing that, Ayman. So you get this. Is this clear to everyone? Alright, so তারপরে তোমার যখন power supply বাসা পর্যন্ত আসলো, এখানে এসে you need another transformer. What sort of transformer would you put here? Step down. Why would you put a step down transformer? Because you can't work with this voltage. ঠিক আছে, তুমি মোবাইল চার্জ করতে গেলে এই ভোল্টেজ দিয়ে মোবাইল চার্জ করতে যাও খালি দেখো কি মজাটা হয়, ঠিক আছে? So what you do is you step it down. By what factor would you step it down? Obviously by a factor of 1000. That means the primary coil would have say a million turns, and the secondary coil would have a ratio of say 1000 turns. Do you get it? So this is still a factor of 1000. যত বেশি টার্ন তত বেশি efficient. আমরা চাইলে আমরা বানাইতে পারতাম 1000 turns primary coil আর secondary coil একটা turn, right? But that would create very inefficient transformers. Current flux line গুলা wouldn't cut through the ES so effectively. So we try to put a lot of turns in both of the coils. Right, so step down hole ki hobe, it will go back to the original 240 volts and 10 amperes. তখন গিয়ে তুমি বাসায় সাপ্লাই করতে পারো। ওই যে রাস্তার মুখে দেখো না, ওই যে ট্রান্সফরমার দুদিন পর বাস মারে, পার্টি করে, তারপর মানুষ ঠিক করে কি জানি। So it's more efficient to put transformers একদম রাস্তার মুখে than to actually allow energy loss along the cables. বুঝছো? মানে usually step down happens in stages. First একবার step down হলো ধরো ঢাকা শহরে ঢুকে, আরেকবার স্টেপ ডাউন হলো ধরো গুলশানে ঢুকে, তারপর আরেকটা স্টেপ ডাউন হলো ধরো এই রিজন গুলশান 2, আরেকটা স্টেপ ডাউন হবে এই রাস্তার মাথায়, আরেকটা স্টেপ ডাউন হবে লাইক ক্লোজ টু দ্য বিল্ডিং। ডু ইউ গেট ইট? সো ইট স্টেপস ডাউন ইন স্টেজেস। কেন? ইফ ইউ ওয়ার টু স্টেপ ইট ডাউন একবারে ইন ঢাকা, ওই যে 240 ভোল্ট 10 অ্যাম্পিয়ার যে কারেন্ট ক্যারি করতো যে ওয়্যারটা জাস্ট ফ্রম লাইক দ্য পাওয়ার স্টেশন ইন ঢাকা টু সে গুলশান এই বাসা পর্যন্ত, it would cause what? A huge amount of energy loss ওইখানেই। It's more efficient actually to put a transformer at the front of the building. Do you get it, guys? Is everyone clear on this? So this is why we use transformers, basically to minimize line loss. ঠিক আছে? And how are we doing this? We're decreasing the current. Current decrease করলে power loss ইয়ে হবে. And if you're curious, তোমার v square by r যদি এখানে use করো, again we won't be using 240,000 for v square by r. We would be using the voltage across the cable from this end to that end. So current যদি কমায় দাও, then the energy loss will be less, the PD across the wire will also be less. So that means what? V square by r যদি তুমি পরেও calculate করো, তখন তুমি দেখবা যে voltage changeটা across the wire is actually very small. এত পর্যন্ত clear? Alright, I think I left out this one thing. That is, transformers case, why can't we use the formula V is equal to IR? Okay, বলতে পারবা? Because, yeah, it's two separate circuits. It's because V is equal to IR, তুমি যদি use করো, say you use V is equal to IR for the primary coil, it can't be applied to the secondary coil because they're two separate coils. They're totally two separate circuits. V is equal to IR for this, why does this come up? অনেকে বলে যে আচ্ছা ভোল্টেজ বেড়ে গেলে তো according to V is equal to IR কারেন্টও বাড়তে হবে because the resistance of the wire stays the same. But the thing is that this is true if you increase the supply. এটা যদি তুমি supply বাড়ায় দাও তাহলে এটা বেড়ে যাবে. This won't have an effect if you increase the number of turns in the secondary coil. Secondary coil is a separate circuit. এখানে voltage will be higher, but the current has to be lower to conserve the law of energy, conserve energy basically. Is this clear to everyone? Alright, so we're done with transformers. Let's have a look.
P equals I square R. The energy loss explain.
I square R, I is the current through the lines, R is the resistance of the wires. যেটা দিয়ে পাস করতেছে।
তাহলে রেজিস্ট্যান্স কমবে।
ওয়্যারে তুমি যদি রেজিস্ট্যান্স কমাইতে পারো তাহলে পাওয়ারের লাইন লসও কমবে। But the problem is যে তোমার পাওয়ারের মধ্যে লাইন লস তো আর তুমি কতই কমাবা, যতই মোটা করো না কেন, even if you take like really thick wires, you still have a lot of inefficiency. বুঝছো?
তাহলে মানে P equals I square R এটা দিয়ে
নামিরা
কারেন্ট কমবে যে ইনডিউসার কম হয় এখানে
কারেন্ট তুমি কমাই দিচ্ছ, তাহলে I স্কয়ারের I কমাই দিচ্ছ, R সেম থাকলো, I is much less, তাহলে তোমার কি পাওয়ার আউটপুট টু much less. Do you get it? The power which is the energy loss in the wire, ওইটা কমে যাচ্ছে. Yes.
Voltage parallel with the current is kind of.
Well, you're conserving power. So the power into a transformer must be equal to the power out of a transformer. Right? So if I automatically increase the voltage by increasing the number of turns, এটা বাড়তে হবে due to Faraday's law. Number of turns বাড়াই দিচ্ছি, voltage বাড়তে হবে. But I cannot just create power out of nowhere. So তাহলে কি হবে? To hear this, আমি কি করব? To have the same amount of power, if I increase the voltage by a certain factor, the current must decrease by a certain factor.
I don't know, sir, V square, VI is working on formula. Formula is, VI is formula is I square is right now.
VI use করব না because they're separate circuits. Right? Alright, so transformers is done.